Howdy and welcome back. So let's conclude today's lesson by discussing how we can implement the breadth first search algorithm. I'm going to do this in a more general way, and then I'll talk about one of the fringe cases with that implementation, and then provide an updated pseudocode in terms of how we can satisfactorily implement this algorithm. So, implementing the algorithm, we're going to need to maintain a queue containing the people to visit, and you can use the standard template libraries queue as the data structure for this. And I'm going to consider our cat problem in this pseudocode, but effectively whatever question you're looking to answer about the objects contained within this search would be an appropriate substitute here. So we'll go ahead and start by pushing, say, or enqueuing rather, in this case, myself to the queue. So here's a kind of cleaned up diagram. So we can go ahead and add myself to the queue. And then what I'm going to go ahead and do is dequeue myself off the queue. I can check if myself has a cat or not. You might want to have that self check on your starting location or not, depending on how you'd like to implement this. That's up to you. If that person has a cat or has the properties that you're looking for, you're done. Otherwise, you're going to go ahead and enqueue their neighbors to the queue. And that's going to be allowing us to begin fanning out here. Because if we begin with myself and I don't have the cat, Nathan, Adarsh, and Joan will be added to my queue. And then we'll just go ahead and continue this process. And that dequeuing, notice how the enqueue adds people to the end. Dequeuing removes the person from the front. Cool. Okay, so continuing through this. We're going to just continue this process until either a person with a cat is found or until the queue becomes empty. If we find ourselves with an empty queue, in this particular case, it would be because no one has a cat. Okay, so one special consideration here is that if the graph is undirected, notice here that Nathan and I share Adarsh as a friend. Adarsh would then get added to the queue twice. One when we go ahead and look at my neighbors, a second time when we look at Nathan. And this would cause an infinite loop to occur because you can see here if I add Adarsh and Nathan adds Adarsh and then Adarsh adds me and Nathan, this is just going to continue on infinitely because we will continue to add ourselves because we're all neighbors to one another each time we visit one of these vertices under consideration. Therefore, it is going to be imperative that we track the status of each vertex, or in this case, person, in the graph. And what I mean by status is whether or not we've already encountered them, whether we've seen them, processed them, or if this vertex has not been seen yet during as we flow through our algorithm. So we're going to address this by not only keeping a queue containing the people to visit, but we will also maintain another data structure that's going to store the status of each person. And we can explicitly store this visited and seen status, and I'll get into what the difference is between these two. And then we could effectively implicitly store unseen. So if you think about this and we're storing, I don't know, let's say we're using a map to store the status. If we haven't seen the person, they're not going to be a key value in our map. So it's kind of indicating this implicit unseen status. If we have seen them, the key value would exist and it would map to some sort of value. And that value could either be visited or seen. And we're just going to differentiate the two to allow us to quickly answer the question of whether or not a particular vertex has been processed or not. Okay, so that aside, the algorithm kind of continues as it had before. We're going to dequeue a person off the queue, and we're going to mark that person as visited in that data structure storing the status. We'll then check if the person has a cat or if they meet whatever property we're searching for in our graph. And if the answer is yes, well, we're done. We found what we're looking for. Otherwise, for each neighbor, if the neighbor has not been seen or visited, so this will require a lookup and do that data structure storing the status. So if they're not seen or visited, we're going to add the neighbor to the queue, and then we're going to mark that person as seen. And why we're using seen here, not visited, is to effectively denote whether or not we've seen them in another vertices adjacency list, or if we've actually processed them. And if we have visited them, that's going to indicate that we have gone through and looked at their neighbors and processed their neighbors. So I'm just going to distinguish between the two. I find it helpful because it allows us to quickly look into that data structure and determine where we are in terms of processing each node, and that could be useful in other algorithms. So we'll continue on this process of dequeuing a person, marking them as visited, checking whether or not they meet the search criteria, and then if we haven't seen their neighbors, adding them to the queue and updating their status. And we'll continue this until a person with a cat or that search property is found, or until the queue becomes empty. And in that case, we can conclude that no one has a cat. And that wraps up our implementation of breadth first search. I hope you can see the data structures that you would use to effectively implement this in the C++ language. We will have you implement this algorithm in either an activity or a machine problem here shortly. So just go through this, work out a couple examples by hand, and make sure that you understand how this is working and how it is effectively, again, assuming equal weighted edges, computing a shortest path between two vertices, and then also in the case of determining whether or not a path exists between a set of vertices. So with that, I'll see y'all. Bye-bye.